half solar mass star, which again is typical of stars like the Sun, you see lives now for about 3 billion years, 30 times longer than the 5 solar mass star. It has a red giant branch when it expands up to about 100 times the radius of the Sun. Then it starts burning helium in its center stably until it runs out of helium, has an AGB, loses most of its mass in 10 to the 5 years or so, and ends its life as a 0.58 solar mass carbon-oxygen white dwarf, the core of the AGB star. Now, why have I bothered to give you all these plots of radius as a function of time? Well, let's just, for example, let's have a look at this 1.5 solar mass star. Suppose that this star was born in a binary system where the radius of the Roche lobe was, let's say, 30 solar radii. Okay, so let's look at radius as a function of time here. So the star is born, it has a radius a little bit bigger than that of the Sun, and it spends most of its life sitting there at a little bit bigger than the size of the Sun until it starts to run out of hydrogen in the center and has to begin to burn hydrogen in shells, and that large temperature gradient drives the envelope to expand and become a red giant. And you'll see that if the size of this Roche lobe was about 30 solar radii, that when the star reached this point here, when its radius was about 30 solar radii, it would begin to overflow its Roche lobe, dump material onto the companion star. And its evolution, although the story is a little more complicated, and I'll tell you a little bit more about that, essentially the evolution is truncated at that point. And you'll see that the composition of the star then is that all of its envelope would get lost from the system, and what would be left would be the core of this red giant at the moment when it started to fill its Roche lobe. And the core of that star, I've plotted core mass in the dotted lines over here, the core of that star is about a 0.2 solar mass helium white dwarf. Okay, so this would end its life as a 0.2 solar mass helium white dwarf. And it's a helium white dwarf because the evolution has been truncated at the time when the star had exhausted hydrogen in its center, is burning hydrogen in shells around the outside, there's no carbon been formed, so it ends its life as a helium white dwarf, and essentially all of the envelope outside this degenerate core would get lost to the companion. Okay. Now, suppose that instead I put exactly the same star in a binary whose size, whose Roche lobe for this star was about 300 solar radii. So binary separation 10 times bigger than the last one. And you remember last time I told you that the probability of making binaries with separations was roughly equal for every decade in separation. So these systems are just as common as these. Well, now let's look what happens. So the star evolves, it exhausts hydrogen in the center, it swells up to become a red giant, but when it's a red giant, it's only about 150 solar radii. Doesn't fill the Roche lobe, no mass transfer. So it happily finishes its red giant evolution, starts burning like helium stably in the center, and lives for another few 100 million years, burning helium in its center, and then it exhausts helium in the center and begins to swell up. But, oh gosh, it gets up to a size of 400 solar radii. So before it gets that big, while it's on the AGB, it will start to transfer its mass to the companion. And now the mass will be lost to the companion, and the final state is going to be not the final 0.58, but a little bit before that, let's say a 0.5 solar mass. But now this star is finished burning helium in its center. It's burned the helium in the center to carbon-oxygen, so it's a 0.5 solar mass carbon-oxygen white dwarf is the final state. Okay. So you can see that the final state is going to depend quite sensitively on the evolution, and the mass of the final star will depend quite sensitively on the evolution. Now, so far I haven't said anything about what happens to all of this other mass, or what happens to the orbit, or what happens to the other star, and all of that is quite important. Oh, and I should say, if the system had started off in a system where the Roche lobe was 3,000 solar radii, the next factor of 10 up, it would have just gone through its whole evolution and ended up as the usual 0.58 solar mass white dwarf without ever transferring any mass to the companion. So from the point of view of trying to do something interesting with the evolution, we're interested in systems where the Roche lobe radii are less than the maximum radii of the stars in these model evolutions, and you can see that that's typically about at best 1,000 solar radii. So why do stars come into contact? Well, the one case I've told you about is radius expansion due to nuclear evolution. As the stars evolve, they tend to have to become convective in their outer parts and develop large envelopes, so the radii expand. But another way that you could make the stars come into contact was you could keep the star at a fixed size and shrink the Roche lobe, and that means shrinking the orbit. And shrinking the orbit corresponds to angular momentum loss. So you shrink the size of the Roche lobe. And there are two ways in which you might lose angular momentum. One is through gravitational radiation. That's important at very short orbital periods. But another one, which is believed to be more important for most stars of non-degenerate sort, is magnetic wind breaking. And of course there's magnetic fields in here, so that means you should not expect very precise calculations. And the idea of this is that if the stars are close enough that they can tidally synchronize each other, so just as the Earth, the Moon orbit, the Earth is not tidally synchronized with the Moon, but the Moon is tidally synchronized with the Earth. We'll see the same face of the Moon pointing to the Earth, so the rotation period of the Moon is equal to its orbital period. So it always keeps the same face. And that's been synchronized due to the Earth's tides dissipating energy in the Moon. And if the Moon were not synchronized, the Moon would be rotating through the tidal deformation of the Earth, caused by the Earth, and that would dissipate energy, and eventually the only steady state solution is when they're tidally locked. Now, if I have the star which is tidally locked to its rotation period, so its rotation period is equal to the orbital period, and that star has a wind, then the wind will be removing angular momentum from the star. If the wind is magnetic, the effective radius from which the angular momentum is removed is not just the radius of the star, but it's the Alfvén radius of the wind. And so the specific angular momentum of the material which is lost in the wind is not the radius of the star times omega squared, but it's the Alfvén radius times the omega squared. And this Alfvén radius will depend on the strength of the star's magnetic field, but typically could be, for example, in the case of the sun, it's 10 or 20 times the radius of the sun. So that corresponds to a rate of loss of angular momentum from the system, which is given by the mass loss rate in the wind times this expression. And that's a J dot, which can remove angular momentum just as in the gravitational radiation case. And that can become quite large for short period binaries, essentially because the omegas become large as the orbital periods get shorter, the star is tidally locked. And so as the binary shrinks, the orbital frequency keeps increasing and the angular momentum rate keeps increasing. Okay. Okay, so some of the important issues before the stars come into contact, one of the first one is whether the stars are actually tidally synchronized or not, because that decides whether the magnetic braking is important. If they're not synchronized, the star could have an omega much less than the orbital frequency, and therefore very little angular momentum loss. Another important issue before the Roche lobe contact, so issues are synchronization, circularization. Remember I told you last time that the typical distribution of eccentricities that stars are formed with is f of e is 2e dE is 2e dE. So the mean eccentricity of the typical binary star is 0.7. That means its pericenter is 0.3 over 1.7, or about 15% of its semi-major axis. So the orbits of the typical initial stars are really quite heavily eccentric. But the orbits of most of these systems, in particular these systems, the double white dwarfs, are all perfectly circular so far as we can tell, and most of the neutron star white dwarf systems are also circular. So it's clear that there's strong effects circularizing binaries, and short period binaries are circularized essentially by this same tidal dissipation. If the orbit is eccentric, there's a time-dependent tide, and that will dissipate energy. Typically synchronization happens first and then circularization. But the tidal dissipation is quite sensitive to the structure of the stars. For example, it's probably much more effective in convective stars than it is in radiative stars, and it's not very well understood. And it turns out that this is really quite important in deciding things like the stability of mass transfer. And another possibility which wasn't taken seriously until a couple of years ago when it became clear that it was absolutely necessary to explain the observations, is that if you have some process which would like to drive a wind off the star, as the star starts to approach its Roche lobe, you can think in some sense as if the binding energy that you have to give to some material in order to get it off the star, you don't actually have to get it from the star to infinity anymore. You just have to get it from the star to the Roche lobe. And as the star starts to get close to the Roche lobe, it doesn't take very much at all to drive the material off the star. So you might expect that the rates of mass loss from stars that were already losing some material before they started swelling up might be strongly enhanced as they started to approach the Roche lobe. And that might lead, for example, to very large angular momentum loss, and therefore a large change in the orbital angular momentum, therefore the separation of the two stars, and changes in the mass of the star. Now, after contact, so when one star has filled its Roche lobe and begun to transfer material to the other star, there are many more difficult issues, namely what happens to the mass in the angular momentum. And there are a number of possibilities. One is that it's accreted with little change in the recipient. Okay, so the one star loses the mass, the other gains it, but nothing very special happens to it, it just gets more massive. Another possibility is that most of the mass is blown out in a wind, either directly from the Roche lobe, from outside the Roche lobe, or from the accretion disk that forms around the companion. And each of those three choices produces a very different J dot, and therefore a very different orbital evolution. One is that it's accreted but swells the recipient to fill its Roche lobe, or it's accreted but blown out in nova explosions. So this is relevant for white dwarfs and possibly for some kinds of neutron stars. If the material accretes on the surface, say you're accreting hydrogen or helium, you pile up a layer on the surface of the star until there's so much material that the bottom of it's hot enough that it ignites fusion. It's degenerate ignition that blows off the accreted material and perhaps a little bit more of the star. So you might actually completely disrupt the stars eventually. Now, what can happen to the angular momentum? Two standard possibilities are that it's transferred back to the mass donor via the viscosity in an accretion disk, followed by tidal coupling at the outer edge of the disk. So a slightly eccentric disk is a tidal coupling. Tidal torque is exerted between the disk and the donor star. That's one possibility. And another possibility is that most of the angular momentum is lost with the mass in the wind. Another question which is important for the mass transfer is the mass transfer stable? I said the mass got transferred from one star to the other. Is it transferred on the time scale it takes the radius to swell, which is a nuclear time scale? Is it transferred on a time it takes radiation to leak out of the star? That's a thermal time scale, much shorter. Or is it transferred in just a few orbits? All three of those cases occur in nature. And we'll figure out why. So it can occur on dynamical time scale, on the thermal time scale, and on the nuclear time scale. And if it's unstable, important questions are, does the system form a stable common envelope? And such stars exist. This W Uma star here, CC Commi, consists of two stars which have one common convective envelope around it. There are two stars burning hydrogen in their centers, and there's a common convective envelope around them, which is shaped like a two-lobe pear. It just happily goes round and round, and they seem to live for 10 to the 8th years like that. Spectacular. So that would be a stable common envelope. Well, what's believed to happen for most of the systems we're interested in is that such an envelope forms, but then one star is orbiting faster than the rotation period of the envelope, and so there's a huge gas drag which drags this star in a few orbits. So large gas drag leads to spiral in. And now there are two possibilities. One is the star could spiral in, and that enormous drag leads to heating of the envelope, and it could eject the envelope, leaving this star orbiting the core of the other one. So leaving a tight binary. But another thing that could happen is either this star doesn't actually have enough orbital energy to unbind the envelope, or it could happen that the density profile is so shallow that as the star comes in, there's no clear end point for the evolution. There's no real difference between a core and an envelope, and then this star will just keep going until it gets to the center of the other star, and the two stars will merge. Now, I've listed these as questions. There is not one answer to these questions. The answer to every one of those questions is yes. in some cases. It happens on the dynamical timescale, it happens on the thermal timescale, it happens on the nuclear timescale. Sometimes they form a stable common envelope, sometimes they spiral in, sometimes the envelope gets ejected, sometimes it doesn't get ejected and they merge. Sometimes all of these things happen too. Depends on the circumstances, and you have to do a detailed analysis and have physical intuition, knowledge of the observations, and some good guesswork through computer simulations to decide which one happens when. So it's not very simple to decide what happens in all of these cases. And because it's not simple, that also means that in some of these cases there are actually people who believe different things. So let me just give you one very simple example to address this question about whether the mass transfer is stable. So let's suppose the mass transfer initially is due to nuclear evolution. No angular momentum loss, the star is just swelling up till it fills its rush lobe. And let's suppose that the star which is swelling is one of mass little m, which is much less than the mass of its companion, which is big M. This is not a necessary assumption, this is just to make things very simple algebraically on the board. So let's suppose that m plus m is conserved. So everything's accreted by the companion, no winds carrying anything off. And let's assume that the angular momentum is conserved. In the angular momentum, anybody know in our solar system where most of the angular momentum is? It's not in the sun, it's in Jupiter. And the reason is, of course, that so there's angular momentum in the sun, but you have to ask who's sent. The sun is also going in a little circle associated with Jupiter, but the sun is going in a little circle whose radius is 1/1000th that of Jupiter, and its velocity in the little circle is 1/1000th of Jupiter because it's going in 1/1000th the radius with the same 5-year orbit, 12-year orbital period. Okay, so the angular momentum per unit mass, which is v times r, the specific angular momentum of the sun is 10 to the minus 6 that of Jupiter, but its mass is 1,000 times larger, so its total orbital angular momentum of the sun about the solar system barycenter is 1/1000th the orbital angular momentum of Jupiter around the sun. Okay. So in this limit, the two orbital angular momenta hits mainly in the light body, and therefore the angular momentum, if the semi-major axis is a, is square root of gm over a. That's a times square root of gm over a times little m. It's mostly in the small body. Okay. So let's consider two cases. Let's suppose the first case that we transfer mass from m onto big M. Okay, so this little star fills its rush lobe and starts dumping onto the heavier star. Okay, now the mass, M is much bigger than M, so the mass of this big one doesn't change very much when this one dumps its mass on, so this big M is fixed. But little m is going down, so that means A must go up to keep angular momentum conserved. So J equals constant, because I'm assuming that everything's going through an accretion disk, and the accretion disk carrying the viscosity out, and then a tidal coupling puts it back in the little m. That means that A goes like m to the minus 2, which means that the rush lobe goes like m to the minus 5/3. Remember, in that limit, the radius of the rush lobe is given by gm over r squared is like gm over a cubed r, so the rush lobe is like a m over m to the 1/3. Okay, so as the mass goes down, as mass is transferred, the rush lobe expands. Okay. So that's a good thing, right? I take a little bit of mass off, the rush lobe gets bigger, so unless the star gets a whole lot bigger when it loses mass, that's stable transfer. But let's suppose that I now transfer from the heavy star to the light one. Okay, J equals constant, A goes like m to the minus 2, so RL, the rush lobe of the big star, which is filling its rush lobe, is going proportional again to m to the minus 2, but remember it's the big one that's losing mass, so this is shrinking really fast. Right? So this is proportional to 1 over m naught plus m naught minus m squared. So this shrinks fast. And that sounds kind of bad, right? I take a little mass off the big star, put it on the little one, and the orbit shrinks. And now this big star was filling its rush lobe, but the orbit is shrunk, so now it's really overflowing its rush lobe. Well, that sounds like a recipe for instability. So we now have to compare this. So the question is, this tells you how the rush lobe changes, and what we now have to ask is, how does the size of the star in equilibrium change when we remove a little bit of mass? So you can imagine removing the mass on a time scale so quickly that the star doesn't have time to transfer radiation through it, so no change, time scale much less than the thermal time scale. And then what we care about is the log of the radius of the star, the log of its mass at fixed entropy and composition. And if that's less than zeta L, which is defined as the log of the rush lobe, the log of the mass, then as M1 drops, the stellar radius is decreasing less rapidly than the rush lobe radius. And that means that the outer parts of the star are going to flow away at the sound speed, and so that leads to a dynamical runaway. Conversely, if it were the other way around, it would be stable. So for white dwarfs and red giants that are fully convective, white dwarf and red giants, the radius goes like mass to the minus 1/3. So zeta adiabatic is minus 1/3. So transfer from the less massive component, zeta L is minus 5/3, is then stable on a dynamical time scale. That transfer from the more massive component, so zeta L is 2m over m, which is much bigger than 1, is unstable. So for these white dwarfs and red giants, you remove a little bit of mass, the star gets a little bit bigger, but not nearly as fast as the rush lobe gets bigger if it's the less massive one that's losing, but the rush lobe is shrinking in the other case. So this is dynamically unstable. So these are sort of two extreme limits, and there's an actual critical mass ratio, so that's the mass of the loser over the mass of the gainer, and that's 0.63 is the critical value, and if the mass ratio is less than this, you're stable. Above that, you're unstable. For white dwarfs, main sequence are low mass main sequence stars and 0.8 for helium stars. Now, it turns out that for stars with radiative envelopes, the radiative envelope means it's is stable against convection, which means the entropy is larger in the outer parts of the star. So when you lose mass, you're losing the high entropy bits of the star, leaving behind lower entropy bits of the star. And that means for radiative stars, unlike these convective or degeneracy pressure supported ones, the star generally shrinks quite dramatically when you remove mass from it, because you're taking off the high entropy pieces. So they shrink when you remove mass. And typical value is zeta adiabatic is about 8. So if you look up here, you see that I can afford to have a mass ratio of 4 before I go unstable for a radiative, dynamically unstable for a radiative star. Okay, so I could have a star that was 2 or 3 times more massive, losing mass, and it would still be stable transfer as long as the star that's losing is radiative, as opposed to convective or degeneracy pressure supported. So if it's unstable, once the star that's losing material finds itself inside the material of the other star, orbiting inside the other star, now there's a large gas drag, so-called common envelope. And a necessary but not sufficient condition that the common envelope actually be expelled, leaving behind a smaller binary that's ejected the envelope, is that the binding energy of the envelope, which is usually written as G over lambda. So this is the star with the large envelope, that binding energy be less than the, written as a positive number, be less than the change in the binding energy of the binary. In other words, the 2 stars come in, the change in the orbital energy exceeds the binding energy of the star, and that's minus 1/2 core mass of the 2 stars divided by the initial semi-major axis. Oops, now let's do this one more. And typically, AF is much less than AI. And one common prescription is to say that you determine these final radii by saying that a fraction alpha CE of this change in the binding energy goes into removing the envelope. So if you calculate the initial mass and radius of this star, lambda is a number of ordinary unity that tells you about the central concentration of the envelope to get the binding energy. This then is a prescription for determining the final radius in terms of the initial one. And let me just give you a very simple cottage history of one binary star. Yep. Okay. So shall I save my toy example for the beginning of next time, or? Okay. Okay. So this example starts off as a 2.5 solar mass star and a 1.1 solar mass star with an orbital period of just under a year. An initial separation A is 288 solar radii. After 628 megayears, this star, the more massive one, evolves first and becomes an AGB star, and it fills its rush lobe, just like the example I gave you over there. Since this is the more massive star, and it's a giant star, this is unstable transfer, same description I just gave. And you can then work out what the binding energy of this star's envelope is from that formula and find out what the final separation has to be. And the final separation is 6 solar radii. And the envelope of this star is ejected, so it ends up as a 0.6 solar mass carbon-oxygen white dwarf. This star is still a 1.1 solar mass main sequence star, which shrunk in, still fits inside its rush lobe. After 7929 megayears, this star begins to evolve, and at 6 solar radii, it comes into contact while it's in the Hertzsprung gap. So And this transfer, now this star is more massive than this one, is unstable. And this star then ends up as a 0.4 solar mass helium white dwarf. That's the core of this star when it hasn't even quite become a giant yet. And the final radius in order to eject this envelope is now 0.6 solar radii. So now I have a 0.6 solar mass carbon-oxygen white dwarf orbiting a 0.14 solar mass helium white dwarf with an orbital period of about 1,000 seconds. Very tight binary. Okay, now this binary now, this white dwarf, which is the bigger one, is not filling its rush lobe, but after only 8614 megayears, gravitational radiation has removed enough angular momentum that this white dwarf begins to fill its rush lobe and dump material onto the other one. So gravitational radiation in this star inexorably evolves over the rest of the universe, so up to 15 gigayears. It evolves from 0.14 solar masses to 0.01 solar masses, and the period minimum when it fills its rush lobe is 0.09 R solar radii. And then when it fills its rush lobe, this is now a less massive white dwarf transferring to a more massive one. That's stable by that prescription, so the orbit just backs out, and it ends up finally at 0.5 solar radii with 1/100th of a solar mass. And during this phase, it's a white dwarf retreating from a low-mass white dwarf, and that's called an AM quantum venaticorum system. And I listed 6 of those systems on this sheet. Okay? So that's an example of one set of this prescriptions.